problem, and this will be the last problem we do, although it is a long one. This will be the last problem we do before we take a break. It says Tumbaga was the name given by Spaniards to a non-specific alloy of gold and copper, which they found in widespread use in pre-Columbian Mesoamerica and South America. The proportion of gold to copper in artifacts varies widely. Items have been found with as much as 97% gold, while others instead contain 97% copper. And that text was from Wikipedia. A 4.84 gram sample of Tumbaga was submitted for analysis. You put the sample into a concentrated nitric acid, where the copper, but not the gold, reacts with nitric acid via an oxidation-reduction reaction to produce NO2, a poisonous brown gas, and H2O. The NO2, also called nitrogen dioxide, is collected at 25 degrees Celsius over water. Remember that gas collected over water means, and we'll talk about that in a minute, and these little symbols are supposed to be quotation marks, but they did not transfer into this homework system. The collected gas occupies 617.1 milliliters at a total pressure of 726 millimeters of mercury. Calculate the percent copper by mass in the sample. Assume that all of the copper in the sample dissolves. You upload your work. Please show your work and submit as a PDF file. And lo and behold, here is the balanced reaction, which we will need to do this. And the first thing I'll say about this is a very wordy problem, and we're going to have to figure out what all these things mean. I will point out to you, so the term collected over water does mean that the total pressure is going to equal the partial pressure of our gas, nitrogen dioxide, plus the partial pressure of H2O, which we just practiced looking up, and we called it the vapor pressure. And so I'm writing vapor pressure, look it up, and we'll go back to that table in a minute. So that's what collected over water means. Other things we have is we have a sample size. Sample size. We have a temperature. I don't know what happened to the units there, but we have a volume. Temperature is 25 degrees Celsius. We have a volume, and we have a pressure. And that's a total pressure. Okay, so that's all we have. And the question, what we're looking for here, is the percent copper. Let's see. Question mark. Now, here's a little bit more about how to I would approach the calculations. So we know that we have some nitrogen dioxide, and we have to figure out how much. And nitrogen dioxide is a product. And we're trying to figure out the percent copper, which means we need grams of copper here. So we're going to have to do some stoichiometry, some calculations involving mole to mole coefficients. And then whatever mass we get here for our mass of copper, we divide it by our mass of our sample to get our percent copper. Okay? So that's our overall approach to this question. Now, in order to figure out the moles of gas for our nitrogen dioxide, we are going to have to use the volume, the temperature, and the pressure, although not the total pressure, the pressure of just the nitrogen dioxide. So let's figure that out first. So our total pressure is 726 millimeters of mercury. Our partial pressure of nitrogen dioxide is the unknown. And then we look up our partial pressure of H2O. Um, and our partial pressure of H2O at the temperature in our problem, 25 degrees Celsius. Our partial pressure of H2O is 23.78 millimeters of mercury. So, and now it's pretty straightforward to solve for our partial pressure of nitrogen dioxide. My O looks a little small. I'll make it a little bigger there, NO2. Subtract the 23.78 off of the 726. I get rounded to 3 sig figs 702 as millimeters of mercury. And if we're going to use the ideal gas law in a few minutes, we have to turn our pressure, partial pressure, in from millimeters of mercury into atmospheres. (760 millimeters of mercury in 1 atmosphere). And my partial pressure is 0.924 atmospheres. Okay. So, and again, what we're trying to do is we're trying to find out our moles of nitrogen dioxide. So we can do stoichiometry to find out how much copper we must have started with in order to produce that much nitrogen dioxide. We're going to be using the ideal gas law. For the ideal gas law, we're going to be personalizing it for the partial pressure of nitrogen dioxide to equal the moles of nitrogen dioxide. The ideal gas law works the same no matter what. You don't have to specify this, but I like to. Now what I'm going to do is I'm going to plug everything in. I have 0.924 atmospheres. My volume, which according to the ideal gas law must be in liters, I have 617.1 milliliters. That's 0.6171 liters. I don't know my moles of nitrogen dioxide. I do know my R, 0.08206 liter atmospheres per mole Kelvin. Those are all of the units that have to be in this equation. And my temperature, which is 25 degrees Celsius, add 273 to that, you get 298. 298 Kelvin is what that says there. Then I can rearrange to solve for my moles of nitrogen dioxide. And then plugging everything in, I get 0.924 times 0.6171 divided by R and T. I get 0.0233 moles of nitrogen dioxide. And I don't have to write this, but those are the moles of nitrogen dioxide produced via this reaction. I now know that there's a 2-to-1 mole ratio. To get from moles of nitrogen dioxide to moles of copper.
Professor, can you just push the sheet up? Thank you.
Yep. From there, I know since I'm going to grams of copper, I have to get my periodic table and see that there are 63.55 grams of copper per mole. And that will give me grams of copper. Let me multiply that all out. 0.0233 divided by 2 times 63.55. I get 0.740 grams of copper. And I'm not done yet because it says calculate the percent copper by mass in the sample. And I know that my sample way up here is 4.84 grams. So my percent copper is going to be equal to my grams of copper divided by my grams of sample. Times 100%. Oh, sorry, I wrote my answer wrong there. So my calculator, and I do this from time to time, my calculator says 0.740. There we go. Sorry about that. 0.740. Now I'll fix my calculation. So easy to do, by the way. I know, right? And then my sample is 4.84 grams. Times it by 100%. And I get divided by 4.84 times it by 100, 15.3% copper. And that is my final answer here. That is the answer that we're looking for. That is the only thing that we're looking for. And that is quite a problem, I know. Any questions about it? It's a lot to process too. Well, what I'll do is, it is break time. We've been going for over an hour, so I'm going to take a 10-minute break. It's 1:36, probably almost 1:37. So 1:47. Let's see.